Okay, for this video, we'll be going through electromagnetism. So make sure you have your notes. So these are the success criteria. Okay, I'll try to record the videos in terms of success criteria. Yep. Okay, so let's start with the first one. You must be able to draw the pattern of the magnetic field due to current in straight wires. Okay, and in solenoids. So solenoids, we actually did it in the previous chapter. Remember the right hand grip rule? So for solenoid, if I were to draw the right hand, it will look like this. Okay, so this is the right hand. Okay, and this is the thumb, right? So this is the right hand grip rule. So for solenoid, the fingernails represent the current. Okay, and the thumb points in the direction of north. Alright, so later we'll be going through the right hand grip rule for solenoid. Okay, and state the effect on the magnetic field of changing the magnetic or direction of the current. So let's go into the concept. When a current flows, it produces a magnetic field around it. This is very important. So this relationship between current and magnetism is electromagnetism. So it's made up of two words, electro and magnetism. In the previous chapter whereby we were doing magnetism, for magnetism it is actually due to magnets. But now in this chapter we find out that whenever a current flows, it will actually produce a magnetic field around it. So it's not just a magnet that produces a magnetic field. A current that flows through a wire, straight wire, or a solenoid will also produce a magnetic field. And this is the working principle behind this chapter. Okay, so now we talk about current flowing in a straight wire. When a current flows in a straight wire, it produces a magnetic field around the whole length of the wire, forming concentric circles of magnetic field line pattern around the wire. So concentric circles are circles of increasing distance from one another. Okay, so this is a little bit different from your uniform wavefronts, circular wavefronts. Okay, so we learned in previous chapter that whenever the field lines are closer together, it means that the field strengths are stronger, and as the field lines get further and further away, the field strength becomes weaker. Okay, then we talk about we'll be talking about this experiment that somebody, I forgot the name, did in a few, I think many years ago. All right, so basically when if you look at this circuit, when the current is not flowing because there is no the switch is open, the current does not flow, we have a compass B and compass A. Now compass A is above the wire, compass B is below the wire. Okay, as you can see from the subtle difference in their drawing, both compasses are actually pointing to the geographical north. Okay, both are pointing in the geographical north. However, when current flows, because the switch is now closed, the current flows out from the positive terminal, flows through this straight wire. Okay, you'll find that actually both compasses are pointing in opposite direction. Okay, later I'll explain why. And this is another view. Okay, so this is a 3D view. Okay, we find that when there's no current flowing through the straight wire conductor, all the compasses are pointing in the same direction. Okay, however, when a current flows through, you will see that the compass are actually flowing, pointing in different directions, almost as if they are circular. That means if I have this, if I'm going to have many compasses around this, they will actually form a circular direction. Okay. So some important observations: when the cut in B was lowered or raised, the direction of the needles do not change because the current was assumed to be flowing in a certain direction, right, going to the bottom of the page. So this suggests that a magnetic field produced by a conductor or straight wire forms a circle around the conductor. Now when the compasses on the cuts are repositioned further away, the needles again form a circle. So this suggests that the magnetic field produced forms concentric circles. Now, however, when the direction of the current is reversed, the needles will deflect in the opposite direction. So if you were to compare these two diagrams, okay, so for here, it is actually flowing in this direction. Yes, in let's say clockwise. But for here, you see that it's actually flowing in the Okay, sorry for the glitch. You'll find that they are actually flowing in this direction, okay, anti-clockwise, okay, which means when the direction of the current changes, the direction of the magnetic field also changes. Okay, so now we'll go into this right-hand grid rule. It is used to predict the direction of the magnetic field around a wire that carries a current, be it a solenoid or straight wire. So just now I wrote in my previous part, I drew my right hand, okay, gripping something, and my thumb will naturally be pointing in this direction. So this is for right-hand grid rule for solenoid. Okay, for solenoid. Now the direction of the fingers represent the direction of current flowing in the coil. Okay, whereas the thumb represents the direction of north. Okay, so for straight wire, it is different. The direction of the thumb represents current. Okay, compare this with direction of direction of the north in a solenoid. Okay, when you're using right-hand grid rule. For straight wire, the thumb represents direction of current and the fingers represent direction of the magnetic field. Okay, so how do I understand this diagram? Basically, the eye is placed on top of the top part here. Okay, so we are viewing it from the top. So if we are viewing it from the top, we will actually get this diagram. Okay, but before I do that, I need to talk to you about these directions. It is very important. So this arrow is pointing to the top of the page. This arrow is pointing to the bottom. Okay, and this arrow is pointing to the right, and this arrow is pointing to the left. Okay, so this is actually what you already know, but we now include two new directions. This is a dot. Okay, we have a dot and a cross. So the dot actually means something is coming out of the page. Okay, because we are not able to represent something on a flat piece of paper because the paper is 2D. Okay, we can only represent two direction. So what if we want to represent 3D, meaning something that comes out from the paper? We have to use a dot. Okay, so it's as if like I have an arrow, okay, and the arrow, if it's observed from here by this person, right, you will actually see a dot, which means you will see this tip of the arrow. If somebody is observing from the other side, the end of the arrow, he will actually see a cross. So this dot will signify it's going to observer. The direction is going towards observer. This direction of cross is showing going away from observer. Okay, so if you are now drawing a dot and cross over here, the dot will means that the direction signifies something coming out of the page. Now take note that all these arrows, the dot and cross, represents direction. They represents direction. Direction of what? It will depend on the context. It will depend on the question. So all I know is that this arrow is to the top, this is bottom, this is left, this is right. It can be current, it can be magnetic field, it can be force, it can be anything. All right, you have to read the question. So the dot, it represents something, a direction, of something that's coming out of page, and the cross will represent the direction of something going into page. Okay, so if you understand this, we can come back to this example here. Okay, so I position the eye on top. So if I position the eye on top of the wire, I will not be looking at the whole length of the wire. Rather, I'll be looking at a circular cylinder, whereby in this example, the current is coming out and going into the eye. So from the eye's perspective, it will see a dot, and this dot represents the current. Okay, so now we need to apply right hand grip rule for straight wire, because this is current flowing in a straight wire. And the right hand grip rule, the thumb actually represents the direction of the current. Okay, and this dot means it's going into you because it's coming out from the paper. Okay, so then you'll see that if you're using your right hand grip rule now, with your thumb pointing to yourself or the thumb coming out from the page, you will see that your fingers are actually pointing in the anti-clockwise direction. Okay, anti-clockwise direction. How about now the next example, if again the eye is over here. Okay, but in this case, the eye is still placed above the wire, but the wire is moving away from the observer. Okay, so if I were to convert this into a 2D diagram, you will see that it is actually a cross. What does the cross represent? The cross represents going into page. What is going into page? It is now the current that's going into the page. So now your thumb should be pointing into the paper, towards the paper, okay, and not towards yourself. And when you see that, when you do that, you'll see that your fingers are pointing in a clockwise direction, and now the clockwise direction represents the magnetic field. Okay, so please try for these two examples and see whether you can get the magnetic field's direction. Okay, it's very important. Now please take note that the direction of the magnetic field of a current carrying wire reverses when the direction of the current is reversed. This next example, this next diagram shows that when I have stronger current, I2, the magnitude of the current is larger, it will produce a greater concentration of the magnetic field lines. Okay, just to try out your right hand grip rule, your thumb should be pointing out from the page, out from the screen, and then you'll find that your fingers are pointing in the anti-clockwise direction as shown by all these arrows here. Okay, now we go back a little bit on the current flowing a solenoid. So please do not confuse the direction of the thumb. What does it represent? For solenoid, the thumb represents the where the north is. The fingers represent the magnetic field. The fingers represent the current flowing in the solenoid. Okay, this is important. The magnetic field strength in a flat coil or in a coil of wire can be increased by increasing the current. Increasing the number of turns, important. Do not say, it's wrong to say that number of coil. Okay, it's the number of turns. And placing a soft iron core, because the soft iron core is a soft magnetic material, so the purpose is to concentrate the magnetic field lines. Okay, let's go to success criteria B. Okay, describe the application of the magnetic effect of a current in electromagnetics. Okay, circuit breaker. So we have already learned about circuit breaker in practical electricity, but how does it really work? Okay, this diagram actually just shows a certain model of the the circuit breaker. Okay, there can be many other different drawings, but ultimately the concept is the same. Okay, so let us read the steps. Step 1, under normal conditions, when the switch is turned on, current flows through the solenoid. So very important, when current flows, it actually produces a magnetic field. Okay, When current flows, it produces a magnetic field. So let's read number 2. When the current is below the limit, the magnetic field that it produces is weak and does not attract the iron bulk. Where's the iron bulk? This is the switch on. This is the number 2. When current flows, it produces a magnetic field, but it's not strong enough to attract this iron bulk. Okay? So the solenoid and iron bulk are not in contact. So the current flows normally through the circuit. So the current actually flows this way. The switch is on, home appliances, and goes back to the mains. Now, suddenly there's a surge in current when there's an electrical fault. If the surge in current exceeds the limit, the solenoid becomes an electromagnet that's strong enough. Or you can say that it becomes a stronger electromagnet, right? Because if I increase the current, the magnetic field produced by the current will actually be stronger. Okay, the key word here is stronger. You cannot say that if the surge in current exceeds the limit, the solenoid becomes an electromagnet, right? So it was already an electromagnet. It's just that it wasn't strong enough. Why? Because the current is below the circuit breaker limit, right? So what happens now that it becomes a stronger electromagnet? As a result, the plastic plunger is free to move upwards, because before that the plastic plunger was actually stopped by this iron bulk. Okay, but now that the iron bulk moved to the left, right, due to the attraction, and it is an iron bulk. What's the purpose of using iron bulk? Because it is a soft magnetic material. So this thing can happen very quickly because the iron bulk can be easily magnetized, right? So now the plastic plunger is actually free to move upwards. Before that, it was stopped. Okay, as the spring around the plunger extends, there's a spring here, it is relaxed. Over here, it is compressed. Okay, so all the other circuit breaker will work on this same concept. The current is below the limit, right? But when there's an electrical fault, the current becomes stronger, the solenoid becomes a stronger electromagnet. Then something will happen to cause the device to trip. In this case, it's a plastic plunger. So what happens when the plunger moves up? The switch will be turned off, and this results in an open circuit and current no longer flows. Okay, so if let's say now I found where the fault is, I can actually press a reset button. Remember, circuit breaker can be reset, but fuse cannot. Okay, fuse does not work on electromagnetism. Circuit breaker works on electromagnetism. Okay, so there is another one here. Okay, it's actually inside an older textbook. So it is the same concept. Please read through this. The important thing to mention is that it always becomes a stronger electromagnet. Okay, so read through this. Okay, so that's for success criteria B. Okay, I would think I will stop this video now. So this is for success criteria A and B.